space. Here, at least they tried, right? They added.
啊，我刚才乱叫了一通。我先进到我的小 DC 里面，然后啊，身份组，身份组，多加一个，要给我的那个 DC 多加一个身份组。我看一下哦。其实也不用，没关系，就直接给。反正就是有这个身份组的，就是有在开台的。哇，好啦，我要开始布置一下我的学习环境。想说我的 Clip Studio 怎么打不开？好，切桌面看，要这样，这样子，还是这样子？好像其实都没差。为什么脸上会有一行字还是什么的啊？这是真的有一行字在我脸上吗？看一下，真的有一行字更新当前页面快取。不然先把它拉到黑黑的地方，反正它字是黑的。字好像不见了，那就放回来。好，开始吧，希望是看得到的。我的绘图板还没准备好。好，测试一下。声音好像变得有点远。关系，问题很快就会改观。在看谁说话？什么声音？等等。 开始。
The factor of c to turn this into meters. So everything on this side is meters. Here, that's in seconds and that's in meters, and the price you pay is you get these weird c squares in there. We're not going to do any of that because everything we're going to do is like I showed you before with the matrix notation. There's another formalism out there that involves something called the rapidity. We're not going to implement that very much.
挑我最喜欢的颜色。
Not critical for QED prerequisites, but it is important to know that there's, this is an equivalent mathematical formulation that just sort of takes advantage of the properties of these hyperbolic functions. And so we want to create this matrix that that generalizes this. For the way what we mean by generalize this is I want B to be a vector that boosts in an arbitrary direction. So I want B to be bx
应该看2部影片吧，看一下哦。
plus by times
对啊，我先把那个
plus bz times
它的准备中的那个需要准备的知识里的那个导论之变换解决掉啊。
You frequently see t, x, y, z. But for QED, in order to grow into that subject, we really do want to go with x0,
没关系，我先把它的东西写下来。
x3. We want to do that. So this would actually be something like this. Beta 0, x0 hat, beta 1, x1 hat, beta 2. These betas aren't, these should be betas, right? These are all betas. B is our magnetic field, right? So this is supposed to be beta, right? Beta, beta. Terrible betas, but they're all supposed to be betas, right? Just like that. So we want to, a general story is a general boost in a general direction, but it doesn't involve a rotation, right? There's no rotation here. So what we have in this circumstance is we have the S frame here and the S prime frame, which is, co-located, but here's a few moments later after it's left, and its boost B, beta, is in some arbitrary direction, right? And so in this notation here, the author that did this, which I think this might have actually come right out of Jackson. I think Jackson definitely has this matrix in it. Jackson is the electromagnetics book for most graduate students.
等一下哦，应该跳到大概这里。
Mechanics and electromagnetism. It's always the Z using a matrix multiplication side is and the S beta 2. These betas, I want B to be a vector that boosts in an arbitrary direction. So I want B to be bx times x hat plus by times y hat plus bz times z hat. And that's using this XYZ coordinate system, which is done a lot in special relativity. If all you're doing is special relativity, you frequently see T, X, Y, Z. But for QED, in order to grow into that subject, we really do want to go with X0, X1, X2, and X3. We want to do that. So this would actually be something like
我等下看一下他怎么说。我要再听一次。
These betas aren't. These should be betas, right? These are all betas. B is our magnetic field, right? So this is supposed to be beta, right? Beta, beta. Terrible betas, but they're all supposed to be betas, right? Just like that. So we want to. So a general story is a general boost in a general direction, but it doesn't involve a rotation, right? There's no rotation here. So what we have in this circumstance is we have the S frame here and the S field, right? So this is supposed to be T, X, Y, Z.
再来一次，我再听一次。
But for QED, in order to grow into that subject, we really do want to go with X0, X1, X2, and X3. We want to do that. So this would actually be something like this. Beta 0, X0 hat, beta 1, X1 hat, beta 2. these betas aren't. These should be betas, right? These are all betas. B is our magnetic field, right? So this is supposed to be
哦，他只是说 B 会被以为是
terrible betas, but they're all
磁
supposed to
场
be betas, right? Just like that.
只是他说的 B 是
So
下
we
面
want
的
to,
贝
so
塔。
a general story is a general boost in a general direction, but it doesn't involve a rotation, right? There's no rotation here. So what we have in this circumstance is we have the S frame here
先
and
把这些
the
抄下
S
来。
prime frame, which is, co-located, but here's a few moments later after it's left, and its boost B, beta
抱歉
is in some
写得有点丑
arbitrary direction. Right? And so in this notation here,
是
the
X
author
真的
did
是
this, which I think this might have actually come right out of Jackson. I think
X 真的是
Jackson definitely has this
到底哪个
matrix in
希
it.
腊人
Jackson
我
is
觉
the
得
electromagnetics
这个
book
字很
for
好
graduate
写啊。
students. But so here what you see is what we would replace V over C with beta X, and we replace Vy over C with beta Y, and Vz over C with beta Z, right? And V would just be replaced by beta dot beta, right? V squared would be. And likewise over here, these all become just, your beta Z, beta Y, beta X. And so this is, and that would become, and this is also what we're going to call lambda AB, right? Or I guess lambda, that's actually technically not correct, because if I write lambda AB, I'm thinking of the AB component, but here I'm trying to talk about the whole matrix. So I would actually do something a little more like this. I would write it as just lambda of beta, right? Lambda is a function of beta. And that's lambda is the standard, Lorentz transformation in almost all QED books. And I included this little picture here because I wanted to show you how this is kind of created, what we'll do in order to produce lambda of beta. This now will just be replaced by
请你回去一
beta
下
dot beta, right?
再回去一点点
V squared would be. And likewise over here. So in this notation here, the author that did this, which I think this might have actually come right out of Jackson. I think Jackson definitely has this matrix in it. Jackson is the electromagnetics book for most graduate students. So here what you see is what we would replace V over C with beta X, and we replace Vy over C with beta Y, and Vz over C with beta Z, right? And V would just be replaced by beta dot beta, right? V squared would be.
我在想我要不要把这个矩阵才弄下来
Z, beta Y, beta X. And
看一下哦。抄下来，这矩阵我抄下来一下。B1伽马。啊，给的空间不太够。 没关系，给大一点的空间。或者说干脆直接不要写这里好了。所以说这矩阵是在说 A 都，等一下哦。在它的坐标系里面转换到我们的坐标系里面，看起来会长什么样 ？OK， 完了，太久没有写伽马。伽马 I 除 C， 再来负伽马 VC 除 C。哇，这矩阵原来长得那么丑啊！VC， VXVZ。一平，然后这里伽马减1，BYBC 除以 B 平，然后这里是1加伽马减1，伽马减1。这里是 x 平，所以说这里就是 y 平。伽马减1，然后 xc， 所以 vyvc。伽马减1，哦，超大一串。啊，终于写完了，然后记得给它加个框框。所以如果把 B 丢进去，等一下哦。如果把这个 B， 把这个，如果人在这里， 然后我们把这些向量丢进去，所以其实这里应该要写 b plot。现在向量丢进去，得出来的结果就是它在我们这个坐标系里面看起来的样子 s prime。
So this is, and that would become, and this is also what we're going to call lambda AB, right? Or I guess lambda, that's actually technically not correct, because if I write lambda AB, I'm thinking of the AB component, but here I'm trying to talk about the whole matrix. So I would actually do something a little more like this. I would write it as just lambda of beta, right? Lambda is a function of beta. And that's lambda is the standard, Lorentz transformation in almost all QED books.
我不能写
And I included this little picture here because I wanted to show you how this is kind of created. What we'll do in order to produce lambda of beta, this now is our final notation, is we'll essentially execute a rotation of the 4 vector through the polar coordinates of beta. So we rotate it so that it aligns the z-axis. This alignment, if these polar coordinates of beta, right? Lambda is a function of beta.
Beta 乘 b.
And that's lambda is the standard, Lorentz transformation in almost all QED books. And I included this little picture here because I wanted to show you how this is kind of created. What we'll do in order to produce lambda of beta, this now is our final notation, is we'll essentially execute a rotation of the 4 vector through the polar coordinates of beta. Beta.
1加伽马减1，然后它这里写贝塔乘 b。我想一下，是对的吗？OK， 然后这个东西丢进去的话。贝塔。easy， 然后应该不能只写贝塔乘 b 啦，它应该是说这些东西都是贝塔乘 b 的一部分。这样子的话，我这里其实也可以加上 b。
Beta, right? Lambda is a function of beta. And that's lambda is the standard, Lorentz transformation in almost all QED books. And I included this little picture here because I must be replaced by beta dot and the s hat plus bz times z hat. And that's using this sort of z. But for QED, in order to grow into actually be, E is our magnetic field, right? So this is supposed to be beta, right? Beta.
Okay, 它把全部都改成 beta.
There's no rotation here. So what we have to do to boost transformation along the z-axis, and then you unwind the original rotation. So you're not doing any net rotation, but you are boosting in your arbitrary direction. And if you take those matrices and you do things one by one, right? You do the first rotation
boost
of the first polar coordinate,
在
the
这里
second
就
rotation
是
on the second polar coordinate. You execute the boost, which in this case they're
坐标
using
轴
the
变换
hyperbolic notation for the boost, right? And we'll talk about this in a moment. We'll kind of demonstrate how this works in a moment. And then you unwind it. You end up with this very tricky, elaborate matrix, but it's all just trigonomic conversion between polar and rectilinear coordinates, and using these definitions of the rapidity up here, right?
它把这些塞进去就会变成
gamma is cosh of the rapidity. And when you do that, you can just convert, and you end up with
它把这些塞进去就会
what
变
we
成这
actually
个
like, which is this guy right here. This is what when I say, look, we're going to boost with the Lorentz transformation, a pure Lorentz boost. We're going to talk about this thing, a pure Lorentz boost. Why is it pure? It's pure because there's no
那我这边要截图。档案读取图像。它怎么那么黑？这个好，这不属于那个什么，不属于图层，它不给色调补偿。加了。
rotation involved. This is just this boost in some direction beta. And notice that it's symmetric. Really important point. It is perfectly symmetric. All of these guys are equal. This guy here is identical to this guy there. This author, in order to stress the symmetry of it, there's a tendency to want to put y first and x second in this case. Or no, x first, y second, and then y first, x second. But he straightened them all out. So the symmetry is totally evident, even though these are just numbers, right? So these are just component numbers, so they commute. But he's made it really evident that these are all symmetric. And that's how you tell that you have a pure boost. And that's an important point. You tell that it's a pure boost because your Lorentz transformation matrix, lambda, is symmetric like this. I should be careful. There might be some symmetric matrices for Lorentz boosts that are not pure boosts. But let's put it this way. If it's a pure boost, then it's symmetric. How about that? We'll say it that. I'll reserve the if and only if when I'm a little more comfortable with it. But if it's a pure boost in any arbitrary direction, this matrix will be symmetric. Now, the reason we're after that is ultimately we want to talk about Thomas precession, right? And Thomas precession involves the transformation matrices that you might think are boosts and you might think should be pure boosts, but aren't because the resulting matrix is not symmetric. So it involves a boost and a rotation. And that's an important thing to discover. And we're going to walk down the road of discovery to understand how that works in special relativity. So when we reach relativistic quantum mechanics and we discover Thomas precession is built in, we're like, wow, we're amazed because we understand it and we're expecting it. So just to be clear, let's take this matrix here and use it to derive these very elementary expressions. Let's see how those things line up. All right? And the way we're going to do that is by simple matrix multiplication. So we understand that this is the Lorentz transformation from the lab frame to the moving frame. We understand that we're working to achieve that elementary result, which only involved a boost in the x direction. So what that means is that beta as a vector is just beta x.
它那边会有乌鸦的声音啊。
X, I guess that'd be x1 hat, right? So it's just beta x. So beta y and beta z are 0. So we immediately cross out all the terms that don't just involve
因为它这边只有假设
So all these terms are 0,
那个
0, 0, 0, 0.
它假设这个惯 S plot 这个惯性坐标系只有往 x 方向做移动，所以这些东西全部都可以去掉，它们都是0。
That leaves behind 1, right? So this guy is actually 1 is still there. Same thing. This term goes away, but you have 1 here. And then this term, right? Beta x equals beta. So this is 1. So you get 1 plus gamma minus 1. So all that's left
这我之后再去看一下要怎么
gamma, but the rest of these guys
要怎么推导好。
So what does this mean for our matrix multiplication? Right? So now we just execute the matrix multiplication with what's left. And what do we get? And what you
不然
get
它
is
这样
this
子结
expression
果
right
论
here.
性的塞
We
进
notice
去，我
right
自
away
己
x2
是
and
不
x3
太
are
能
not
接受。
transformed. Right? So this, I guess I should write down that this is equal to x0 prime, x1 prime, x2 prime, and x3 prime, right? So we now have x0 prime equals this expression here, gamma x0 minus gamma beta x x1. And gamma x0, this is x0, minus beta gamma x1. So that's a match. And then we have x1 prime equals minus gamma beta x x0 plus gamma x1. And going up here, we have plus gamma x1 minus gamma beta x0.
那我这里好像不应该写这个。
So we've got a match, right? So the point is that this complex matrix simplifies radically to now turn that sort of formulaic elementary view into just matrix algebra, and that's really important. However, this doesn't solve every problem, right? Because all this does is it takes points in the lab frame and gives you points in the moving frame. If you considered the moving frame the lab frame, then all we have to do is change the sign of beta x to minus beta x, and we will actually get the inverse of this matrix. That will drive a matrix inverse. Usually it's very difficult to find the inverse of a matrix. If someone just showed this to you and said, hey, you know, what is the inverse of this matrix here, right? If they said, you know, here's a matrix, find the inverse.
我已经忘记3乘3的反函数
All you got to do
矩
is
阵要
change,
怎么
in this case, all you have to do is change
要
the
怎么做
sign
啊？
of beta x, beta y, and beta z, and
何况4乘4。
So that's a nice convenient thing that's characteristic of these Lorentz transformations. All right, so from now on, this is how anybody who's marching down the road to learning quantum field theory or QED or anything like that must think about Lorentz transformations of 4 vectors, right? Of 4 vectors. The problem, of course, is that there are many more objects in the universe than 4 vectors, right? There are spinners, which we talked about. There are bispinners, right? Bispinners, which we will talk about when we study the Dirac equation, right? There are higher dimensional vectors. There are all kinds of objects in the world that are not 4 vectors and yet model physical things and exist in space-time or are placed in space-time by our models. And when we execute a Lorentz transformation, these guys have to also be transformed, right? They also have to follow the new boosted reference frame. So we know how to transform 4 vectors, right? But we don't necessarily know how to transform these other objects. And as we encounter them, we always must learn how do they transform under a Lorentz transformation. Because if these things are going to be part of physical law, they have to be able to be boosted around from one frame to another. That's the rule of special relativity. No frame is special. If I write down a formula of physics in one frame, I should
哦，
transfer
这
it to another
个
frame and get the same formula. So if a spinner represents something physical,
什
I
么
have
都
to
要
be able to
转换
transform
哎
it from one frame to another. Now, we already saw in our last lecture about spinners
啊，
how we
好
were
有
able to
趣哦。
take the rotations of an object in three-dimensional space and sort of bootstrap that to figure out how spinners rotated in three-dimensional space. And yes, the principle is always sort of similar when we determine how these things transform. But we're going to worry about that later. The point I'm trying to understand is we have not mastered the art of the Lorentz transformation. Mastering the art of the Lorentz transformation means that you can take any object, any mathematical object that represents something physical, and transform it from one frame to a boosted frame. And right now, we've really just focused on 4 vectors. And actually, right now, that's all we're going to need, right? That's all we're going to need. But we now want to talk a little bit about
完
understanding
了，我觉得我
differences
之后一直
between
回来看这一
different
部
frames
哎。
and relative motion. So the rest of this lecture is going to be a little bit of a fun review of some of the ways of looking at special relativity and understanding length contraction and time dilation and space-like separation and time-like separation. So if you feel good with all that stuff, you can skip it, but I find it really fun, so we're going to do it. So we need to graduate our understanding from this high school version of
What's
S
material
prime,
to
y and x-axis, and a y prime,
your
and a
voice?
prime axis moving at a
Hey.
random velocity, and we need to pump ourselves up into the Minkowski diagram. The big deal being that this y is now replaced by t, and what we're going to show is that the S prime coordinate system has this deformation, and it's now represented by this deformed coordinate system that appears to be non-orthogonal, but it actually, we're still treating it as orthogonal. And in the S prime system, all the points along this X prime axis, right, are points that exist at constant time. And all the points that exist along this line are points that exist at constant position. Now, the constant position. Now, understand this means constant position in S prime. So that means you're moving, or if you're following this line in space-time, you're moving. We're co-moving with the S prime coordinate system, and in this coordinate system, you have 0 motion. So you're actually attached to the S prime coordinate system.
Time.
And motion that is attached to the S prime coordinate system can be understood as any motion in this diagram that is parallel to this constant position line. So there, for example, I have drawn a small semi-grid of constant position lines. So I can imagine that if you are a particle in this system, and there you are, and you are motionless in the S prime system, then as time advances, or as t prime advances, you will move along this line. And obviously, in the S system, this will appear to be
这条线是 S prime 坐标系的 x 轴，这条线是 S prime 坐标系的时间要怎么说 ？S prime 坐标系的时间轴，所以这两条线对于 S prime 来说是互相垂直的。当然对 S 来说应该也要是垂直的啦。我想一下哦，会是垂直的吗？会啦。如果是光的话。
motion that is completely attached to the S prime system moving along, right? So you will see motion starting here and then moving here like that, right? And so that's the way we understand constant position in the moving frame. What's a little less obvious is, or a little less intuitive, is to understand a constant time movement. So what do we mean by a constant time movement? Well, obviously it's not a physical movement because you can't move from one place to another in any reference frame without moving in time. So for example, if this point is considered as a point in the lab frame, right, its constant position motion would be straight like that, right? And clearly its constant position motion in the lab frame is cutting across lines of constant position in the moving frame, and so clearly it demonstrates motion in the moving frame, and that motion is actually backwards, right? So that's important. But you certainly wouldn't imagine a particle in the lab frames moving like this, because it's changing position without changing time, right? Now, such a motion or such an interval does make mathematical sense, and it's called space-like, and we'll talk about that in a moment. But the point is this is not to understand it to mean motion, but if you are this particle and you're wondering about all of the places in space that are occurring right now for you, simultaneous to you, you are looking at this horizontal slice of the Minkowski diagram, meaning any other particle that's out there that's on this slice is whatever's happening to that particle.
它对他来说，就是在他坐标系里面，在他坐标系里面有，我看一下哦，这个对他来说，在他的坐标系里面已经往他自己的时间的反方向走了，所以不太可能。
It's happening simultaneously to whatever is happening to you, right? If this is you, and this is some other point in space-time, these things are happening simultaneous. It is a mistake to say that, it's commonly understood that, simultaneity was destroyed by special relativity, and that's not true, right? Simultaneity is a thing, right? Simultaneity is this plane is a plane of simultaneous events relative to the lab frame, right? Relative to the lab frame, these things are simultaneous. Likewise, relative to the moving frame, right? Anything that's along a line that is parallel to this x prime axis, those events are simultaneous relative to the lab. And I've drawn in these lines of constant time slice in the moving frame, right? Lines of constant time slice in the lab frame are just horizontal lines.
对啊，如果他照他刚才的走法的话，
matters, right?
他会回溯到，
It's just not
他会回溯
invariant, because obviously what is simultaneous in the moving frame is not simultaneous in the lab frame. So this is an example of a property of the world
应该是我一直都想要开啦，
or it's not covariant, or
只是想到
when you make a Lorentz
我可能进去应该会先去刷怪， 练个等， 应该会很无聊，所以我就没开了。
So that is what was destroyed, is universal simultaneity. There is no universal simultaneity. So that was destroyed. But the idea of being simultaneous is absolutely critical to the way you observe the world in your own
我删的不会啦，我这台电脑
Minkowski diagram, for example, if I take a
那个什么
point here in
磁碟2 TB，
and I say I want a simultaneous point in the moving frame, so I take one right here.
有些感觉会继续玩的，我就不会删。
In the moving frame, these are two simultaneous things. These two events are happening at the same instant. But clearly, they're happening at different times in the lab frame. And this is the basis of all of the amazing, fun, special relativity paradoxes. Is that simultaneity is not a thing.
学长教我相对论
paradoxes out there. But the fun ones, like we'll do one in a moment, the rod and barn paradox, for example, is quickly put to to rest by understanding that simultaneity is not a universal concept. And this is important in QED because there are these things called equal time commutation relations. And those equal time commutation relations depend on being in a certain frame and having a sense of simultaneity. So we're now going to put some bones on this coordinate system to see how it's developed and how it's derived from a given circumstance. First of all, we need to understand that we are presuming that beta, the boost that connects the lab frame S with the moving frame S prime, is just in the x direction, which is why only the x-axis is deformed with the t prime axis, right? And the matrix that we learned about, of course, we were all proud of how general this was, right? We could boost in any direction. But unfortunately, to use these diagrams, we still have to kind of focus on a single axis. Now, we could have aligned this with B and done it arbitrarily, but then that axis would have been the one deformed.
对，我等下开法环，我应该也要开小黄鸭。
And all of everything would be just sort of out of whack. So we're just going to choose the direction to be x, and we're going to boost in the x direction. And now we're going to put bones on the system by, we're going to tick out.
虽然不知道那个 frame 会不会整个乱掉。
1 unit of distance, 2 units of distance, 3 units of distance, and then there's got to be 1 unit of time, 2 units of time, 3 units of time. But of course, with c equals 1, everything will be, I'll just use the word meters, right? Everything will be in meters, and including time, right? So I guess, to be completely together with my original notion, I should label this the x0 axis, right? And then this should be the x1 prime axis, and this should be the x1 axis, something like that. But we need to figure out if this is a meter in the moving frame, right? Or if this is a meter of time, or if this is a meter of space in the moving frame, where do I put my ticks on the non-moving frame? You might think, oh, we're just going to rotate the axis. So we would, just sort of follow a circular thing, and then that's the spot. That's 1, but that's not the way it's done. It's all hyperbolic geometry, so everything is a little bit screwy. So how do we lay out these coordinates in a way that's consistent with Lorentzian geometry? Well, I'm going to use a slightly different approach here because I really want to exercise this matrix as much as I can, because that's what I want you to get out of all this, is thinking of Lorentzian in terms of a matrix lambda.
有一个图形是有一个玩具，它下面它就是展示坐标轴如何变换，然后它下面的卡槽都是双曲线。
What 1 meter looks like in the rest frame. This now looks like a x prime, but it's the number 1, and then this here is the way this is supposed to read is x1 prime, like that. That's the notation that I'm kind of shooting for here. You know what? Let's just go back to, see, this is why we need to be flexible, right? I'm just going to go back with time and x and t prime and x prime, right? Okay, so we are allowed to arbitrarily choose how to lay out a 1 meter. But what is important is that everybody agrees on what a meter is, right? And everybody agrees on what a meter of time is, or I guess what I should say is everybody agrees on what the speed of light is, and everybody agrees, everybody's got the same clock, the same metering stick. So we all meet up before S prime gets sent off in the x direction at speed beta x, and we share meter sticks and we share clocks, so everybody's got the same clock device, the same meter stick, right? And that meter stick in this unmoving frame has this length, right? Just some arbitrary length there. So now the question is all right, so this is a point that in the non-moving frame, this point here has coordinates, and those coordinates are literally t equals 0, x equals 1, y equals 0, and z equals 0. So now the question is what are the coordinates of this point, which I'll mark in blue, in the x prime coordinate system, right? And we are going to just use our Lorentz transformation matrix to figure that out, right? We go over here and we put in the point.
我明明才刚醒，为什么会一直打哈欠？
1, 0, 0. That is a
还
point
是
in
说睡
space-time
只是睡30 分钟，
And now we
不
look
太够
at
吧？
our Lorentz transformation matrix, and we know that everything that has a by in it is 0. So we get rid of all of this stuff and just keep that 1. Everything that has a bz in it is 0, so we get rid of all that stuff and just keep the 1. Likewise, we get rid of this, and we get rid of this. And then here, in this one, this becomes 1, right? Because beta equals beta x in our simple transformation. So that is 1. So we get 1 minus 1, and all we do is keep a gamma, and the rest of it sort of goes away. So with that in mind, this matrix multiplication becomes very easy. And we just work it out that we end up with minus gamma beta x and gamma 0, 0. So the point that is represented by 0, 1, 0, 0 in the lab frame is minus gamma beta x gamma in the moving frame. Now gamma, we know, is the square root of 1 minus beta squared. That's going to be greater than, whoops, not greater than 0, definitely greater than 0, but it's actually going to be greater than 1. Remember, beta is less than 1 and greater than negative 1.
它的时间在 gamma bx
so the absolute value of this number will be smaller than the absolute value of this number. In other words, beta x is less than 1, so clearly the absolute value of the time component is less than gamma. So this is the coordinates in the moving frame. So now we know that this point's coordinates in the moving frame have to be gamma, or have to be minus beta x gamma and gamma. Well, where is that spot? Well, how do we see that geometrically, right? Well, geometrically, I'll just extend these coordinates a little bit. So geometrically, what I want to do to find the coordinate values is I need to extend lines parallel to the coordinate axis through this point. So with a parallel line with the t prime axis intersects x there, and a parallel line with the x prime axis intersects t there, right? So I know that this has got to be gamma, and that's got to be minus beta x times gamma. And then the coordinate of this point in the green system, or in the moving system, is minus beta x gamma, gamma 0, 0. And this is true for any 4 vector. You can just run this transformation and get the new components in the moving system. So
所以我们
what does
是
this
看
tell us?
到
Well,
它
gamma
的
is
过
bigger
去
than 1,
是
so we
吗？
know the value of 1
很
on
合
the x
理。
prime axis has to be somewhere along this line to the left of gamma, right?
星光到我们眼里要时间，确实。
Now, but we can run the logic in reverse, right? We can now say, all right, well, let's say this point here. Let's figure out where is 1. Well, if this point was 1, if we did this in the reverse order, right? And we instead of taking 1, 0, 1, 0, 0 from the stationary frame to the rest frame to the moving frame, we did it from the moving frame back to the rest frame, then we would start with 0, 1, 0, 0 in the moving frame, and we're asking what is it in the rest frame. Well, we can do that too. So we go back to this matrix up here, and we erase the black stuff, right? And we draw in the green, right? Which obviously is just purely symbolic, just so you know which way we're headed. But now we need the inverse Lorentz transformation, right? We need the transformation that goes the other way. But that's not very difficult. It's barely an inconvenience, in fact, right? we just switch the sign of those two things because all we're doing is changing the direction of beta x. Beta x doesn't appear anywhere else in these matrix elements. And so when we do that and we execute this multiplication, everything turns out to be the same.
直接翻过来就好了。
And so if we go back down here and we did the same geometric rule,
应该只有在那个特定情况下才能这样子翻呢。
Right? And we would say, oh, well, that's got to be gamma, right? Because that's how we figure out the x coordinate. And we extend a line parallel to x, and that is beta x gamma, which is, of course, exactly what we calculated right here. And so we kind of see the relationship between where these points have to be. The value of 1 on x prime has to be to the right of this vertical here that I'm indicating, but it has to be the left of this vertical, so it has to be sort of in this zone. And because the gammas always have to be to the right of 1. And
所以就是说，他们看我们在伽马的位置，我们看他也在伽马的位置，他的坐标轴上的伽马位置。那在他的坐标轴上看我们的话，我们的时间会被他觉得是在然后这样子转换下来的话，我们时间会被他们感觉是在贝塔伽马那边，然后他们的时间对我们来说是在负贝塔伽马那里。那这样子是这样，他们看见我们未来了，不对吧？我想一下哦。这个过来，然后这一点啊，不能这样看啊，等一下哦。这一点，对他来，我看一下哦，可能对他来说在伽马，对。一个点，他也觉得我们在伽马点，然后在负的贝塔伽马点，的时间，那我们看他的会觉得他的他会觉得这个点在伽马的点，然后反过来我们会觉得他的时间会比我们再多一点点。我想一下哦。我们的时间序，他离我，他是在动的那一个，所以说他们看我们跟我们看他们。应该是要一样啦，至少在位置上是一样的。时间的部分的话，我们在0点的时间会被他觉得是负的，因为确实是负的。那他在他自己0点的时间， 会被我们觉得是正的吗？我看一下，正的吗？时间不对，这时间可能只能当参考用的，毕竟尺度都一样。相对于，它的1点，它的1对于我们来说是过了贝塔 x 伽马的时间，那我们的1对它来说是负的贝塔伽马。帮我稍作转换。好，没问题。如果是 S 变成在移动的人的话，确实也会看到正的啊，正的贝塔 x，是这样吗？其实负的啊，哎，真的，不要怀疑，继续。
And there you have it, right? So this is sort of how we understand the orientation of things. Now, what about the slope of this line, right? Well, the slope of this line as a geometric quantity, just based on how to draw this line on a piece of paper, is going to be this distance divided by this distance. So the slope of the line is just going to end up being beta x. So that slope is beta x. And so clearly, the faster you go, right, the closer beta x gets to the speed of light, this will tend to the value 1, and these two green axes will become more and more skewed. And they can become arbitrarily close together, but they can never actually be 45 degrees. But boy, you can see how extreme things can get as you get close to the speed of light, where these two axes are almost, the diagram becomes basically unworkable, right, at some point, because these lines are just too close together. And that's why these Minkowski diagrams are much more useful for illustrations of things, like we'll do in a moment with the pole and barn paradox. Okay, so this whole exercise can be operated again for the time axis, right? But in that case, what we do is we go with 1, 0, 0, 0, and we find its equivalence. And everything sort of ends up kind of in the same deal, right? If that's 1, you drop, you get gamma, and then you end up with 1 unit of time, right? And then that time parallels up here to gamma, and then of course you end up with this time comes down here to a spatial position of minus beta x gamma. And likewise, this time drops down to beta x gamma. So so that's how we that's how these coordinates are ultimately laid out in the Minkowski spacetime. Oh, and the slope of this is going to be beta x minus 1, right? Rise over run. In this case, the rise is beta x gamma, and no, I'm sorry. The run is beta x gamma, and the rise is gamma. So,
对，所以是
gamma
贝塔分之一。
beta x gamma is 1 over beta x, right? So the slope of this line is 1 over beta x.
然后另一个 x 方的
so let me clean
斜
this
率
up,
是
and now
beta
let's use this
x。
diagram to understand something really simple, like time dilation and length contraction. Well, actually, this
它的声音终于正常了。
so what I've done is I've just cleaned up this picture a little bit, so you can see how this Minkowski diagram works. Understanding that as V approaches C, B approaches 1, and these two lines kind of collapse. This angle gets smaller and smaller, and these lines collapse to a single 45-degree line. When you get to really high betas, this diagram isn't very helpful. You lose the ability to actually work with it. But in the next lesson, what we'll do is we'll see how we can extract length contraction and time dilation from this diagram, and then we will begin looking at a couple of the key paradoxes of special relativity through this diagram, which is fun. The first one is just a simple exercise in simultaneity. It's called the barn and pole paradox. But the second one is critical for our understanding of how an electron behaves in a magnetic field, and is definitely prerequisite to QED. And that one, and that material's prerequisite to QED. And the paradox that helps us understand that is called the rod and ring paradox. So we'll attack those in the next lesson.
Go.
Relativity quite a bit, but this one is really important.
这有几分钟啊？
From using
49分钟。
tools. And the properties I want to discuss today are length contraction, very famous property, time dilation, which is perhaps even more famous. The reason time dilation would be more famous than length contraction is we actually measure this routinely in the lab. Length contraction is, involving measuring rods moving near the speed of light. It's kind of hard to get your handle around how an experiment would measure it, but it can. I mean, the implications of length contraction are clearly something we can discuss. It is relevant to our notion of transformation of magnetic and electric fields. So this is an observable effect. But this one is really observable because we can measure time very well. And it's just experimentally seems to be something more attackable. But then I also, once we nail those two things down, I want to talk about the barn pole paradox. We want to use this Minkowski diagram to resolve the barn pole paradox. And I want to at least set up a lesser known but very important paradox, the rod ring paradox. This one you probably have never heard of, unless you've studied special relativity quite a bit. But this one is really important because it sets us up to understand Thomas precession. In other words, the resolution of this paradox involves observing a rotation that is a non-intuitive rotation. And when I say non-intuitive rotation, I mean after you've developed the intuition of special relativity, then a non-intuitive thing pops up, right? So it's kind of fun. All right, so let's begin with length contraction. So to start this discussion, we have to understand that when we're talking about length contraction, we need to be dealing with an extended physical object. For purposes of illustration, we need to demonstrate, and we need to use an extended physical object. Length contraction is much more fundamental than that. Literally, space is being contracted, but we're going to demonstrate it with an extended physical object. And somehow that helps us understand that space itself has this property of contracting. Moving rods look short, right? But when I say look, that implies there's some kind of illusion. Moving rods are short, and that's part of the barn pole paradox, is to show that moving rods are in fact short. So, so by showing that a moving physical object is shortened, that somehow really should be, the point of that is to emphasize that space itself is being shortened. Because goodness knows if you shorten a physical object, then how could you do that uniformly unless something's going on with space itself? So that's the idea. So we're going to work with an extended physical object. But this, of course, begs the question, well, demands the question, how do we represent an extended physical object on a space-time diagram? What do we mean by this? Because what's the alternative, by the way, right? We deal with objects in special relativity all the time. And the alternative, of course, is a particle, right? A particle, it's still a physical object, but it's not extended, right? And so a particle really is easy to put on a space-time diagram because a particle occupies a place on the space-time diagram. You know, the particle has coordinates in the lab frame, and it has coordinates in the moving frame, right? These two are the coordinates in the moving frame, and these two values are the coordinates in the lab frame. So it's easy to locate a particle. But, you know, so now say the particle is some kind of object. Well, you know, can I just put it arbitrarily on the diagram? And if I do, what does that exactly mean? And this is tricky, right? Because if you just take seriously what I just drew, right, you would say, well, the left end of this is very well fixed. It's got good coordinates, unambiguous coordinates in both frames of reference. You know, the right-hand side also has unambiguous coordinates in both frames of reference, right? I can draw these lines on the right-hand side, and I can tell you the exact point, the exact space-time point for that in both systems, right? The way I've drawn it, it's kind of parallel to the...
总之，这个就是在 S-Plane 的惯性坐标轴、惯性坐标系里面，因为 S-Plane 在动嘛，所以说它时间越久，对我们来说，它移动的就越多。可是对 S-Plane 来说，它没有在动，可是它确实有经过一些时间。那我们这边也有经过一些时间，只是它经过的时间会比较，等一下，我看一下，会比较。这样看起来的话，会比较短一点。
The time axis there, but you know, I can still find the coordinates of any 2 points. I can take any 2 points, right, and I can attach them with a line and say there's a material point at every spot here, and there's an extended physical object. So, you know, that is doable and it is allowable, but it's really not what we're after. Because when we think of an extended physical object that we're observing, we want to mean something a little bit more strict. So if I put one end of our rod, our extended physical rod, at the origin, t equals 0 and x equals 0, when I talk about the object as a thing that's undergoing physics, I'm talking about the object as it exists in one full slice of time. That is, an extended physical object, as I want to describe it now, has to lie at one time. Every point on this object has to exist at different points in space because it is, after all, extended, right? But it has to exist at the same time. We're talking about the object as it exists at one moment of simultaneity. So this counts as a good space-time indication of an extended physical object because every point on the physical object exists at a simultaneous moment. Now, this is arranged, this is a space-like interval, right? This point is not in any kind of communication with this point because this is beyond a 45-degree line in this diagram. And you remember, you know, that's the speed of light, right? So nothing from this point can communicate with that point. And that brings us into a whole different and fascinating subject that I don't know much about, but it's called, I think it's loosely called the relativistic theory of elasticity, right? Where we're talking about, you know, the speed of sound in this object is finite. And so the speed of sound can only propagate like, well, it can only propagate kind of like this, you know, something above 45 degrees. So a signal from here can only get to here in a certain amount of time, right? But the whole object itself, right, the whole object itself, whoops, can move through space-time along some world line as long as that world line is not going beyond 45 degrees, right, this object can just move, well, presumably up. You can't go backwards in time, right? But you can move up along the world line, or if you're attached to the S prime frame, you move like this, right? The left-hand side is always staying at x equals 0 in the moving frame, and it's advancing in time, right? That's a perfectly allowable movement. But the whole thing moves together as a slice of time in the frame of the lab. Remember, this we're calling the lab frame. X is the lab frame. So that's what we mean by an extended physical object, is it has to exist at a slice in time. So how would that work for the moving frame? Well, clearly an extended physical object if I lay out an extended physical object in the stationary frame, then there's an issue, because in the moving frame, an extended physical object has got to be, oops, I don't want to change the size too much, has got to be, let's see, I've got to orient it so it's in a constant time slice of the moving frame. So that's what an extended physical object would look like in the moving frame, because all the points are at the same time, right? They exist all at the same time. So if it was to demonstrate movement, let me get rid of that. So if we were to demonstrate movement in the moving frame, or if we were to demonstrate how it appears in the moving frame, right? It's stationary in the moving frame. So this motion here is stationary in the moving frame. But notice at every instant in time, it exists as every point on this object exists at the same time. So clearly the issue is that an object that is an extended physical object on our diagram in this frame doesn't really count as an extended physical object in the other frame, and that's because clearly this guy has a different there's two different times, right? There's this, the right end of the rod and the left end of the rod are at two different times. And so it's kind of like you're looking at a rod at one moment, and then you're considering the left end of if in the stationary frame or the lab frame, you're considering the left end of the rod at one time and the right end of the rod at some other time. And that just doesn't make sense for a physical object. So our issue now is converting this extended physical object to the extended physical object you would observe on the ground, right? And this one here we call the proper one, right? Because any object that is an extended physical object in its own rest frame, that's the proper length of the object, right? So I'm going to call this L0 perhaps, right? Because this is in the frame where this object is at rest, and that's usually what we call the proper length of things when we're talking about pure length. So the length of this in the rest frame is L0. Now the question is well, when I find the equivalent physical object in this frame, right, it's going to be some other extension. Now it's kind of obvious what's going to happen, right? This is going to be projected back, and that's going to be, and this length is going to be the length of the object, and the factor is going to be 1 over gamma, right? So the extended physical object's length in the lab frame is going to end up being 1 over gamma L0. But we want to demonstrate that using our matrix mathematics, right? And this isn't just a simple Lorentz transformation, right? This point, when you do a Lorentz, and this is an important thing I notice people struggle with a bit. If I do a Lorentz transformation of every point on this rod, all I'm doing is taking the coordinates of, say, this point here, right? The coordinates of that point are 0, L0, 0, and 0 in the frame of the moving rod, right? In the rest frame of the rod. When I do a Lorentz transformation, all I'm doing is finding this coordinate here and this coordinate here, and I'm just converting it into some time coordinate, some space coordinate, and presumably the other two will remain 0. But that's all the Lorentz transformation does. It just changes the coordinates. It doesn't literally transform. You can't use the Lorentz transformation to somehow turn this rod from the moving frame into the rod of the lab frame. You have to think a little bit differently, right? So we're actually going to kind of work backwards, right? We're going to ask the following question. Given a extended physical object in the lab frame, how do we understand it? How do we understand the length of this object compared to its differential length in the moving frame, which I've actually sort of attached these parallel lines in order to establish the coordinates of this point in the moving frame, which, as you can see clearly here, shows that this is not a true example of an extended physical object in the moving frame. But it does have a spatial extent. I mean, this object here does have a spatial extent given by this coordinate, and it does have a time extent given by this coordinate. So we're going to look for the relationship between these things. And to do this, we are going to use our Lorentz transformation matrix, right? And this is just as before. We kind of cut it down to just this box here. I guess I should mark that. So here we have the gamma matrix. Everything's 0 except 1, 1, gamma, gamma. And this is going from S prime frame to the S frame. So from the moving frame to the stationary frame. And now this is a linear operator, right? This can take a 4 vector and gives you another 4 vector. So we can actually take the 2 points here, the left point and the right point of this object, or any object, right? This actually, what I'm about to write is true for any 2 points. And so what we're going to do is we're going to write this down in the coordinates of the prime frame. We're going to say, well, the left side of this thing has some time coordinate, and the left side of this thing has some space coordinate, right? But, the right side of the thing has a time coordinate, and the right side of the thing has a space coordinate too, in the moving frame, right? And because this is a linear process, if I take the difference between these two, that is fine. The matrix times this, the left side
如果他有动画给我看一下的话，
the matrix times the right side
我应该会比较好理解。
times the difference between the 2 coordinate points, right? So I'm going to write this down now as this left side minus the right side. I'm going to write this down as just delta t prime and delta x prime, right? The change in the t prime axis and the x prime, the t prime coordinates and the x prime coordinates of the points of the object. And then I'm just going to do the math, right? Obviously, I've kind of cleaned this up. It was a little too messy for my taste, right? So I cleaned it up. You just have to track that we're only using this piece of the matrix and these diagonal ones. And then I write down the expressions, right? Delta t is the result of this matrix operation on this vector. And that gives you this expression right here, gamma delta t prime minus gamma beta x delta x prime equals delta t, where this is the time interval that is experienced by the left and right sides of the bar in the stationary frame or in the lab frame. And then if I execute the same matrix operation on the second element of the vector and discover the second element of the vector, I get this expression, which is basically just this line here times these two things right here. And now the point is, now we talk about the extended physical object. I'm only interested in the circumstance where delta t is actually equal to 0, right? I want the resulting bar to have no space, no temporal extent between the left and right sides. I want them to both be at the same slice of time. So if I turn that, I basically set this term to 0, and then I set that equal to that, and then I get an expression for delta t prime in terms of delta x prime, right? And it's forced by my notion of what an extended physical object is. This is where I insert that notion. So I calculate delta t prime. It's just beta x of delta x prime. And then I use this and insert it in here, and now I get an expression for delta x in the lab frame with respect to delta x in the moving frame. And then you just crunch the algebra a little bit, and you get delta x prime gamma 1 minus beta x squared. But if you remember that gamma is 1 over the square root of 1 minus beta x squared, so you now have delta x prime is 1 minus beta x squared over the square root of 1 minus beta x squared, and you end up with delta x prime, or the spatial extent in the moving frame divided by gamma is the spatial extent in the stationary frame. Gamma is a number that's greater than 1. So this spatial extent is less than that spatial extent. And that is the notion of length contraction. And the way this sort of plays out is that it is sort of in the obvious way. I'll just draw it again. In fact, if we reverse this process a little bit, what we'll do is we'll lay the bar out as though it's a extended physical object in the moving frame, and we'll say that it has 1 unit in length. Well, the question is, we take each point on the physical object and we just shift it back to find what is the equivalent point where everything is in the same time slice of the lab frame. And that's not really hard. You just basically you're following a line parallel to the timeline, and you find this point right here, and this becomes the physical object in the lab frame. And we already know that this point here, if you just find its coordinate in the lab frame by just dropping a parallel to the time, you know that this will land at exactly gamma, right? So this
我们会看到
this
这
length
个
here
这个长度的东
is
西
1 divided
沿着
by
这个
gamma, right? So that's
这个
the
长度
point
的
here
东
is that
西
1 divided by gamma.
根据
And that logic is
有一定的速
reflected
度，
in
然后沿着它
mathematics.
另一个坐标系的时间轴，
So here we used our Lorentz
所以才会发
transformation
生
to
delta t
get
这
at
件
it, but
事。
we had to add
OK，
this notion that
我
we're
懂了。
interested only in things that have no temporal extent, only in physical objects where every point on the object on the space-time diagram has the same time in the lab frame. And so a rod that's moving along with 1 full unit in the moving frame, it only has a length of, once we understand it to be a physical object in the stationary frame, its length is actually 1 over gamma. So if we're very close to the speed of light, say, gamma could be 2 or 3 or 4, it can be shrunk to 1/3 of its length, 1/2 of its length. It can be shrunk arbitrarily small. Now notice that if we're dealing with a particle, it becomes kind of a non-thing because it has no extent in either frame, right? Anyway, so that is how length contraction is understood in these Lorentz. It's understood. This is how the calculation is executed. This is what you usually do in special relativity courses, but without the matrix. The matrix is a little heavy-handed tool for this, but I want us to get used to using it. But you can also just sort of see the utility of this Minkowski diagram. And you can also see how hard the Minkowski diagram would be to work if you were going really fast, close to the speed of light, right? And you tried to slip your physical object like this and then draw parallel lines back, and it would be really, really tiny, and everything would be like blown up into the corner. So these Minkowski diagrams are just for, they're very pedagogical in a sense, but you've got to kind of leave these angles. I don't know what speed this angle actually would turn out to be, right? This would be something like, well, maybe we should think about it a little bit. Hold on. Okay, so roughly to my eye, this slope literally turns out to be beta x of 0.444, and that corresponds to a gamma of
0.4光速。
1.12, something like that.
44.4%光速。
Geometric construction is not so far off. Okay, so that's length contraction. Now, the next one we're going to talk about is time dilation, but it's really going to be the same process.
看看
But
是
in
不是又
here,
讲错
instead
了
of having an
没关系
extended
我懂
physical
就好
object that all exists at the same time slice, we're going to demand our clocks stay in the same positions, right? And then, I'm not even going to work the math, but we will do the illustration. So let's do length contraction. Oops, I mean time dilation. So here we start now with two clocks, which I've called the blue clock and the green clock. The blue clock is going to, well, they're both going to start at the same place, but they're in two different frames of reference, right? The green clock is in the moving frame of reference. It's attached to the moving frame, and the blue clock is in the lab. The point is that the blue clock in the lab will be moving, non-moving, I guess. It's moving relative to the moving frame, of course, but it's stationary in the non-moving frame or in the lab frame. So it just follows a world line right up the time axis, right? Just rolls right up the time axis. I keep moving it backwards. Of course, obviously it doesn't move backwards in time, but it moves up. And as it moves, it ticks. Now, let's talk a little bit about clocks, right? What is a clock? Well, a clock is, ultimately a clock is some kind of oscillator and some kind of counter. It oscillates, and it's got to be a good clock, the oscillations have to have uniform periodicity, and to be a meaningful clock, it has to be able to count the number of oscillations that have happened. So an oscillator and a counter. The very most famous one is a nice cesium clock, the typical standard from NIST that is keeping track of everything using physical properties of cesium. We don't need to talk about the nature of a clock, but we do need to understand that when we're talking about this, these two clocks are constructed the same way. They're built the same way. Just like the two measuring rods, a measuring rod moving off with the moving frame and a measuring rod that's left behind, they're the same darn rod, right? Two different copies of the same rod. So how do we know this? Well, everybody starts in the same frame of reference. They both take a clock that's identical. They both take a moving rod that's identical, and off they go. The point is that it's very important to understand that the nature of the clock doesn't matter, because it's not the clock that's being affected. It's not the rod that's being affected. The clocks are running slow not because the clock mechanism is running slow. It's running slow because time is running slow. So your heartbeats are slow. Well, I was going to say your pulse rate, but it's kind of the same thing. Your heart rate is slow. The clock is slow. Everything you see around you is slow, so you don't notice anything. In your proper frame, everything is fine. If time is slowing down, right? If time is slowing down, there's no way to know. But you can look at somebody else's clock, right? The guy at the ground can look at the moving clock and then compare notes, right? And I can compare the marking on my clock with the marking on your clock.
后面会不会更难一点？目前为止
whether your clock is running slower than mine or faster,
还不需要记笔记。
I suppose. And then I can make determinations about how time is flowing in your system, and that's what's going on here. So what's happening is the way we model this time dilation problem is we start in the same position, and this clock moves up to some spot, and we'll call that spot, I don't know, we'll call it 1, right? So after 1, we'll call it 1 meter of time, right? It's like, it should be a second, right? But it's a meter of time. And because every time is at the same units as everything else in this problem. And while it's doing that, this other clock is moving in tandem with the moving frame of reference, right? So there comes a point where the lab clock actually ticks one oscillation or one oscillation count, or I shouldn't say one oscillation. It comes to some, because it's oscillating very fast, right? But so it comes it determines that it's gone at 1 meter of time. And the parallel time slice, I'm interested in what is the marking on this clock over here
吓死我，吓死我！
this same instant in time. As soon as I click 1, I want to know what is happening with this clock at that moment. And, you can tell right away that we already know that there's a point out here, 1 unit of time out, who when I drop down, I get gamma units of time in the lab frame, right? So I know already that this clock has not reached 1 at my simultaneous plane of movement. Now you could ask the question, well, how do you know, right? If you're space-like separated, how do you get a signal from this clock to tell you what time it is? And very sophisticated treatments of this actually deal with that question, right? Because this clock will start sending light signals back, reporting its time, and then you can calculate, you can figure out what was this clock reading when this clock was reading 1. It's not a hard problem. But what we're interested in is what is the simultaneous time slice here? What is this clock reading? And it's obviously reading less than 1. So in the time slices of the lab, you know that the moving clock is running slowly. And that we say moving clock is running slowly, but of course everybody needs to understand time itself is flowing slowly in the moving frame. And you can literally reverse this process, right? You can absolutely reverse this process the following way, right? You now take this clock, you take our 2 clocks, you bring them back to the beginning, and now you're going to be interested in, you're now moving along with the moving clock.
图层每次都没有弄好。
So it's the same argument, right? The moving clock
图层每次都调错。
and while it runs along, the lab clock is running along. But the lab clock we're interested in its parallel time-like slice, right? It's instantaneous slice. They're both stationary, right? They're both at the same position. They're not moving their position. This is always at x prime equals 0 in the moving frame. And in the lab frame, this clock is always at x equals 0. But now we're interested in simultaneous time slices in the moving frame. And those simultaneous time slices are all parallel lines to the x prime axis, right? So we're interested in these parallel lines. So now this clock is here, right? This clock is now on this plane of simultaneity relative to the moving frame. And clearly he's lagging, right? Because, well, I guess I shouldn't say that. What I'll say is that you take this clock and you finally move it up to 1 tick, right? Well, when you move that clock up to 1 tick, this other clock is now down here, and I guess I removed the tick before, so the 1 tick is right about here. I think when I selected it, I selected the tick too. But you can clearly see that this clock has not yet reached 1. So in the frame of in the moving frame, we're calling it, if you are in the moving frame and you look at the simultaneous ticks of the clock that's left behind, you notice that it runs slow. So both sides see the other clock as running slow. It's funny, I didn't do that for the length contraction, but you can show that the length contraction of a moving rod, right? They both perceive the rod as being shorter, right? So they both see contraction. And the issue is that it seems like this is the typical problem with this issue of time dilation is, well, everybody sees everybody else's clocks running slow, and this is the origin of the twin paradox, right? If everybody sees everybody else's clocks running slow, whose clock is actually running slower when you bring 2 twins together? You create that physical situation of undeniable contradiction. And we're not going to go into the twin paradox, but it is definitely something every physicist should be able to explain the twin process. You're not really a physicist if you can't explain these are pretty basic things, actually, time dilation. What we're doing a little differently is we're kind of focusing on this matrix method. And these Minkowski diagrams are not totally typically taught and used all the time. But anyway, So this is the nature of time dilation.
他说，如果你没有办法解释双胞胎悖论，那你就不是物理学家。
is ticking more slowly, and the factor will exactly be gamma.
还行啊，双胞胎悖论。
If we look at this analysis, right, we remember from our previous analysis that this point is in fact 1 over gamma, which is exactly the factor that will slow the clock down. Okay, so that's time dilation. Notice the importance of simultaneity again, right? Simultaneity is important in time dilation. It was important in understanding our physical objects. Simultaneity is what this is all about. So let's review the most famous paradox involving simultaneity in special relativity, the barn and pole paradox. All right, so how does this barn and pole paradox work? It's pretty simple. In fact, it's one of the easiest ones to explain. We imagine ourselves with a barn, and we are standing in the reference frame of the barn, so we're basically on the ground, and the barn has some proper length b0, meaning we're in the rest frame of the barn, we measure the length of the barn, and the length is b0. And there's a rod that is flying towards the barn, and it's flying very quickly, and it has a contraction of gamma. So this rod is L0, the proper length of the rod, divided by gamma long. So this rod is length contracted, because there is some proper length out there where if we were in the reference frame of the rod, it would be length L0. Of course, if we were in the reference frame of the rod, the barn would be moving toward the rod, and the barn would look contracted by the same factor gamma. So these are two different circumstances, as one is viewed by in the stationary frame of the rod, or the proper frame of the rod, and the other is viewed in the proper frame of the barn. The problem is, or the paradox, is that the rod fits inside the barn, and you can close the doors of the barn and actually contain the rod inside the barn, right? And the reason we do this for this paradox is we want to demonstrate that this isn't some illusion, this isn't some trick of the light or some strange effect of visualizing the rod of length 0 and it just appears to be smaller. It's actually smaller. You can close the doors of this barn on both sides, and that rod is length contracted and will fit inside the barn. Case closed, end of story.
Oh.
The paradox, of course, is that if you look at the same analysis where the barn is moving, the barn now moves over the rod, and at no point does the rod ever fit inside the barn. But you are closing the doors of the barn at some point, so what gives?
Right?
And of course what's going to give, just as a spoiler alert, is we close the doors of the barn at the same time.
简单来说，当今天
and we're not closing the doors of the barn at the same time in the reference frame of the rod.
有一辆火车往山洞里面跑，
So let's begin by setting up this.
然后这山洞上面有门会掉下来，是大闸道，它会掉下来。
Meaning the moving frame is moving much faster, and you can tell because this angle is a lot smaller, right? So
这边暂停好了。然后如果它有一个速度的话，那它应该会是那个，假设它原本长度大于那个L0大于这个 L0大于 L， 那它进去的时候，但是它有速度，所以说，那我们看到的可能是这个长度应该会是什么？刚才看好像是贝塔 L 对不对？贝塔 L0，
Beta is a lot steeper, and the paradox, of course, is that.
等一下哦 ，L0除以伽马。 那 L0除以伽马的话， 会小于 L。那如果这个时候我们看到这个东西一进山洞，我们就同时把这两个东西往下放的话，会怎么样？那当然是可以包住它。但是呢，但是如果转换到它的坐标系来看的话，我们的 L 虽然会缩短，但我们时间会变成说，我先看到这个东西放下来，我再看到这个东西放下来。等一下哦。对，先看到它放下来，再看到它放下来。其实我应该用说拿起来比较好吧？没有，就是放下来而已。但是因为某些原因，应该要用那个啊，下去再上去，就是 t 等于0 ，t 等于0，然后假设这个会变成 t plan 等于 a， 它就会变成 pt plan 等于 a 加 delta t。所以它这个隧道就可以，那个一进去，虽然可以对我们来说好像可以关注它，但是对他来说其实是你先这边放了，然后这后面才放。
If you look at the same analysis where the barn is moving, the barn now moves over the rod, and at no point does the rod ever fit inside the barn. But you are closing the doors of the barn at some point, so what gives, right? And of course, what's going to give, just as a spoiler alert, is we close the doors of the barn at the same time in the reference frame of the barn. And we're not closing the doors of the barn at the same time in the reference frame of the rod. And so let's now have a look at how this is resolved using our Minkowski diagram. So let's begin by setting up this Minkowski diagram. So first thing you'll notice is that I've chosen a reference frame for the bar, meaning the moving frame, is moving much faster. And you can tell because this angle is a lot smaller. Right? So beta is a lot steeper. And the diagram's getting to the point where it's almost, this is about as steep as you would want for one of these diagrams to work. Now the barn in the proper, so S is the reference frame of the barn, and the proper frame of the barn, the front side of the barn is given by this straight line. You know, it's never changing its position in the frame of the barn. And likewise, the rear of the barn is also got its constant world line. So those are
虽然说这条线
world lines in the
它是直的，所以代表说它是同时。
Obviously, the barn is moving in.
但是对这个坐标系来说，它的时间却是不一样的点。
The proper length of the barn, we have to get that square. The proper length of the barn is this length right here, right? The barn is an extended object, so we have to use a constant time slice, and that's the proper length of the barn. Now, in this picture, you see that the barn is length contracted. Well, what's the proper length? What is the length of the barn as perceived by the rod? You know, in the rod's frame. Where is that depicted on this diagram? Well, I need a line of constant time, which is any line parallel to this. Remember, this is the x prime axis and the t prime axis. So any line parallel to this x prime axis is a line of constant time. So this is the length. This is the length of the barn in the reference frame of this length here, right? That's the length of the barn in the reference frame of the rod. But now this is where our diagram kind of fails us a little bit, because if you looked at it, you would think, well, this is smaller than this. But we remember how we ticked everything out. Remember, we ticked everything out where we found one unit in the frame of the moving frame was gamma units, which is larger than 1 in the rest frame. So this distance here actually is larger by a factor of gamma to this distance here, which is exactly what this is showing us. The problem is the geometry is hyperbolic, right? So as these lines tilt up towards 45 degrees, these distances actually get smaller, right? And that isn't accounted for very well on this diagram, right? The distances just don't look, all we see Euclidean distances in our head. We can't correct that to make it look shorter. So we actually have to bring some knowledge into this diagram and understand, right, that 1 unit in the moving frame is actually a full gamma units when projected onto the rest frame. And that's why this is actually a foreshortened barn. So this distance here in the moving frame actually does represent this shorter barn. Okay, so now, how do we understand this paradox? Well, let's begin by grabbing our rods. Now, I call them rods because there's a rod that's in the rest frame and a rod that's in the moving frame, but they're the same rod, right? So it's the same rod as understood from the rod's own rest frame and from the frame of the barn. And right away you can see that these rods are represented. This is the Lorentz contracted rod, and this is the proper rod, right? Because it's proper because it's in its own rest frame. The closest you're ever going to get to the notion of a preferred frame in special relativity is the proper frame of something. The problem is that physically that's not particularly preferred, but it is the reference frame of choice to simplify problems as much as you can. So this here is the rod in the equal time slice rod, the extended object in the rest frame of the rod, and this is the extended equal time object in the rest frame of the barn. And you'll notice there's no way of representing that here in this kind of sketch. It really comes out in this Minkowski diagram. So now, how does this thing move? Well, as time goes on, the left side of both rods just stays at a constant position in the moving frame, but is moving to the right in the rest frame. So obviously we're moving this way in the rest frame from left to right, and we're actually stationary in the moving frame, and the barn is moving from right to left.
Yeah, so
what happens is eventually there comes a point in the rod's frame where the rod sees the barn actually cover or cover the front end of the barn actually begins to cover the rod. And that happens right at this point, right? Right at this point. This is the front tip of the rod is now being is fully been approached by the barn, and the barn is now covering the front tip of the rod. And then the rod or the barn then proceeds, and then the back end of the barn then covers the front tip of the rod. And then there's a point where the barn is right over the entirety of the rod. Well, I shouldn't say the entirety, but the rod actually is protruding from both ends of the barn as the barn passes over the rod. And then we get to a point where the rear end of the rod is inside the barn and the front end is out, meaning the front end has left the barn has crossed, the back of the barn has crossed the front end of the rod. It's very tempting to keep saying that the rod is moving, but it's the barn that's moving over the rod, right? And then eventually the barn completely passes the rod. So that's what things look like in the rest frame of the rod. Now in the rest frame of the barn, the rod approaches the barn, right? And now the blue end just enters the barn right there. And then the blue end moves through the barn, and then the left side of the rod enters the barn, and now the rod is fully inside the barn, and then the rod exits the barn. The barn is stationary and the rod moves through. And the idea is that right at this point here, this is where we close the doors. So we close the door there, and we close the door there. Now, we just close it for an instant, right? Because I don't want to get into the story of what happens when the rod hits the door. What if the door is very solid and the rod couldn't bust the door? What would happen then? And that's where we get into the relativistic theory of elasticity. And it's a subject that I just don't want to get into, but it is fascinating. But it all has to do with the fact that the speed of sound in the rod is below the speed of light, and therefore the deceleration of the rod doesn't happen instantaneously. It happens as a matter of time. And then, of course, once you decelerate the rod, it becomes it's switching reference frames now. So it becomes its natural length, but the pulse going through the rod is propagating relatively slowly compared to the motion of the rod, etc., etc., etc. But now we're closing the doors, we're flashing the doors shut just at this instant, just to prove that the rod is inside the barn. Well, of course, flashing them simultaneously is only simultaneous relative to the barn. So what is the flashing times in the frame of the rod, right? What does the rod see? Well, the rod sees this time here is, you have to draw a parallel line to the x-axis, and this is the time where the rod sees the back door shut. And what about the front door? Well, the front door, same thing.
对啊，后面的门会
The rod sees the front door shut somewhere around. Actually, that's probably not.
对那个有速度的惯性坐标系来说，后面的门会
Let me
比
move the rod out of the way.
那个
Let me
前面的人门还要
let me first move this rod
还要
out
快
of the
关上，
way, right?
然后撞到就得
And
爆
let's
开。
draw these lines, right? So these parallel lines are absolutely terrible, right? So hold on. Okay, here's some better parallel lines. So this point, which is at this time here, right, in the Barnes frame, right? Everything happens in the Barnes frame on this simultaneous slice of time, but it actually happens at this time, right? This time here, I'll call that T rear close, and at this time here, that is T front close in the frame of the rod. So now let's go back to seeing how this looks to the rod as the rod's moving. So the rod, so now the barn is approaching the rod, the barn is approaching the rod, the barn is approaching the rod, the barn now crosses the rod, and then at this moment here, the rod sees the front or the rear of the barn flash. It flashes closed and then open. And then the rod proceeds, the rod proceeds, the rod proceeds, the rear now enters, it now enters, or the barn front edge now crosses the rear of the rod, and of course the barn's rear edge has already crossed the front of the rod, right? So the rod's protruding, and then now the rear flashes, right? So the rod is fully past that rear door when it flashes, and then the barn moves across the rod. So you see the simultaneity in the rod's frame, those doors opened and shut in these weird ways. It was approaching the rear of the barn, and then it sees a flash up ahead, but it clears it because the flash is over when the rear of the barn crosses the front of the rod. And likewise, after the rod has passed anything of concern regarding the rear, it's already fully inside the barn, right? So everything looks good to the rod, and it's all about a matter of simultaneity. And these two expressions of what happened are completely legitimate. They're physically totally legitimate. The fact that simultaneity is not a universal thing doesn't matter. There's every conceivable physical phenomenon can be interpreted from both frames of reference, and this rod did in fact fit inside the barn. That's a real effect, right? That is a real thing, and lengths of things are just not relevant in physics. If they were, then there'd be a disaster, right? Because this is a huge circumstance that appears totally differently. So all of physics has to work around this problem. It has to work around the fact that the length of any object is immaterial to the physics, right? The only thing that is material to the physics is the space-time interval of objects, and that space-time interval or of events between events, because that space-time interval is invariant and it can never change. So we have to construct all of our physics around things that are invariant. And the length of objects that are in relative motion, it's not invariant, so you will never see a real physical law where the length of an object can possibly matter. Okay, so that's the barn-pole paradox. Let's see if I have time to set up the rod-ring paradox. Well, no, I don't think I do. So we'll just start with the rod-ring paradox in the next lesson. It's got a lot of meat to it, so we don't want to... We want to do it full justice. So anyway, this is great. I'm hoping that you've enjoyed learning how to use these Minkowski diagrams. Special relativity is really cool. Sorry about begging off the theory of I'm not an expert on the relativistic theory of elasticity, but there are many paradoxes. There's like this bug rivet paradox, which is very fun, but it has to do with the relativistic theory of elasticity as its resolution. And there's this notion, by the way, if you're interested in the subject, it's called Born rigidity. And we are always assuming that we're dealing with things that are born rigid, but there are circumstances where you can't assume that. I think they involve, when you start spinning things, when you take a wheel and you start spinning it relativistically, it gets things get really, really weird. And you don't need to know all of that stuff for special relativity. The stuff for special relativity you need to know. This barn-pole paradox is a definite thing that everybody who claims to understand special relativity must be able to walk through. I mean, that's just de rigueur. Same with length contraction and time dilation. But for our purposes, the most important point, or the important point, is how to use and understand this matrix. Now, this matrix, notice it's a single boost in the beta direction, right? So now we have to talk about multiple boosts, right? And that's going to be the where we start heading with the rod-ring paradox and Thomas precession. But this single boost. I kind of worked through this problem using this matrix. It's a little bit heavy-handed, but I want to make sure everybody's comfortable with these pure Lorentz boosts.
他用的是
Okay, so ring rod paradox next time.
他用的是那个怎么说？他用的坐标系是，笛卡尔坐标系。那如果可以换成圆坐标系吗？好奇。路灯令，觉得我要重开一下直播，顺便改一下标题，稍等一下。